Phylogenetic trees depict relationships between evolving lineages. Different trees imply different sets of relationships. But how can we quantify just how different a pair of trees actually are? Well, measurements of tree similarity underpin a range of lines of scientific inquiry. We can evaluate phylogenetic reconstruction methods by comparing reconstructed trees to a tree that's known to be true. Tree similarity measurements allow us to take the average of a set of trees or to quantify the uncertainty. We could also use these measures to compare evolutionary trajectories between hosts and parasites, or languages and people groups. There's a whole set of things we can do, the list goes on. So it's really important to have a good and meaningful measurement of tree similarity. Well, if your tree has branch lengths or edge lengths, then it's possible to define a continuous space of trees that has some sort of natural geometry by thinking about the difference between a pair of trees as a distance. But edge lengths are often not available or might lack a clear biological meaning, so I'm concerned with differences between unweighted trees where edge lengths have no values or meaning. The most widely used such measure is the Robinson-Foulds distance, which is based on the concept of splits. So each edge in a tree divides the leaves into two partitions or groups. And the Robinson-Foulds distance works by counting the number of splits in one tree that are not also present in the other, and vice versa. One of the many shortcomings with this measure is that nearly identical splits count for nothing. So here I've just made a small edit to the tree. I've moved one leaf to the other side. But there's not one split in this tree that occurs in the second. As a result, these two trees, which agree on most of the relationships between taxa, have the maximum Robinson-Foulds distance. Generalised Robinson-Foulds distances attempt to award some form of credit for similar splits, but there's no natural way of doing this that's yet been proposed. My suggestion is that information theory gives us a way to meaningfully quantify similarity between splits. So I'm going to introduce you quickly to this discipline. So I'd like you to think of a card, any card from a 52 card deck. And I'm going to tell you what card you're thinking of. It's the Jack of Spades. Well, 1 in 52 of you are currently amazed at my powers of guesswork, but all I did there was make a guess. How could I improve my chance of being correct? Well, if you answered a question for me, this would give me some information. I'd be able to make a better guess. And we can quantify information by thinking about how much a new piece of information reduces our uncertainty in an outcome. So if I asked you, is your card red, and you answered yes or no, that would double my chance of guessing correctly. This would yield one bit of information, where a bit of information is defined as enough information to halve the uncertainty. The next concept I want to introduce is entropy. Entropy is the amount of information we expect to gain on average from an answer to a question. And here it's easy to calculate. Whether you answer yes or no, I get one bit of information. So the entropy of this question is 1 bit. But other questions have different entropies. So I could have asked, is your card the Jack of Hearts? And 51 times out of 52 you'd say no, and I'd learn next to nothing. But just occasionally, when your card is the Jack of Hearts, I will learn an awful lot about what your card might be. So the entropy here is quite small, 0.14 bits. This is not as good a question to ask if you want to reduce uncertainty as much as possible. So entropy is the average information gained from a question. The next concept I want to introduce is mutual information. How much information do two questions give in common? So I could ask you two questions now. First, is your card even? Roughly half of cards are, so we get roughly 1 bit of information on average. And then I'm going to ask you whether your card is red. 50-50 chance, 1 bit of information on average. And notice that the value of a card is independent of its colour. So these questions are independent, they have no information in common, and question 2 yields me one bit of genuinely useful new information that narrows down my uncertainty. But I could have asked some different questions. So my first question could have been, is your card greater than 6? Roughly half of cards are, so I get roughly one bit of information. And then I could have asked, is your card greater than 7? Again, roughly half of cards are, I get roughly one bit of information. But these questions are actually very similar, so some of this information is shared between the questions. If, in fact, the card was less than a 6, I'd already know the answer to question 2 before I asked it. So your answer to question 2 is going to gain me no new information. If you said yes to the first question, you've probably got a high card. It's not surprising that your card is greater than a 7. The only case this second question really gives you much information is when you do have a 7, and I get a reasonable amount of information. So I can tot up the average of this, and on average question 2 will give me just 0.3 bits of new information that I didn't already know. Well, hang on, I thought it had an entropy of just about 1 bit. Well, it does, but 0.6 of these bits are just duplicating the information I already had after I'd asked that first question. So this is the mutual information here, is 0.67 bits, and that's the information that these two questions have in common. And you could think of that as measuring the similarity between those two questions. So imagine now that I'm asking you questions, but it's a bit of a noisy phone line, and you might mishear what I'm asking you. So the first question I ask, is your card even? Well, you hear me correctly. So actually the question that I'm asking is the question that you think I'm asking, and there's a lot of mutual information because these are the same question. There's as much mutual information as possible. But next I ask you, is your card greater than 7? And you mishear me. You think I'm asking, is the card greater than 6? So we've just identified that these two questions have a fair bit of information in common. They're quite similar, 0.6 bits. Or I could have asked you, is your card red? And you hear, is your card greater than 7? And we know that the colour of a card has no bearing on its value. These are independent questions. They have no bits of information in common. So we've compared individual questions. We could think of comparing a list of questions with a second list of questions, and all we need to do there is to add up the individual similarity between each pair of questions, and we get a total similarity score for these two lists, here 1.6 bits. So hopefully that gives you a flavour of information theory, but what's this got to do with splits and trees? Well, we can think of a tree as just dividing, a split on a tree as dividing our leaves into two separate partitions. And I could think of this split as a question. I could ask you, is the leaf you're thinking of, pick a leaf, any leaf, is it in the left-hand partition? And if you're thinking of this, if you're looking at the same split as I am, on the same tree as I am, then you're going to understand this question to mean exactly what I understand the question to mean. These two questions have a lot of information in common, the full 0.99 bits. But if you're looking at a different split or a split in a different tree, then your interpretation of the question is going to be slightly different. You'll give the same answer unless you're thinking of leaf A, which is the only leaf I've moved between these two trees. So there's a lot of information in common between these two questions, but not as much as there was before. So we've got slightly less mutual information. These questions, these splits, in other words, are slightly more different. So we can quantify the similarity of two splits. How do we scale up to understand similarity between trees? Well, if we match each split with a similar split and find an optimal matching, here's the splits we just looked at, and we can tot up their mutual information, sum that for all matched splits between two trees, and we get a similarity score. And it can be useful, actually, rather than thinking of similarity, to think of difference, which gives us a distance metric between trees. And we can arrive at that by just summing the non-shared information rather than the shared information. So here's the distance score between these two trees, and notice that it's got a unit. No other distance metric has a meaningful unit associated with it. This is useful. So that's a nice idea. Is this actually useful in practice? Well, there's no objective measure of tree distance, or we wouldn't have to come up with one. So it's a little bit more, we have to be a little bit smart about how we test tree distances. But there are a number of behaviours that we expect a good tree distance to exhibit. So first of all, if I take a leaf in a tree and I move it a short distance, I expect that to produce trees that are more similar, less distant, than trees in which I moved the leaf a long distance, as I have in this comparison tree here. So if I take a number of pairs of trees, I can correlate the distance I've moved a leaf to each of my distance metrics, and the clustering information distance gets things in the right order almost all the time. There's a small amount of error. I've compared this with three other widely used distances. The Robinson-Foulds and the quartet and path have quite different underlying principles, but the quartet and path distance actually don't do particularly well against this test. Alternatively, I might expect that if I move two tips to some other location on the tree, I'm going to get a tree that's more different to the starting tree than if I just move one tip to that same location. And that is indeed the case all the time with the clustering information distance, but the Robinson-Foulds distance never exhibits this expected behaviour. I could also do some more empirical tests. So here I've taken two different trees and I've perturbed each of these trees in order to generate a cluster or group of similar derivative trees. And by measuring the distance between each pair of trees in this simulation, I ought to be able to get back to identify these two separate groups. Now with the clustering information distance, I'm able to do this in a majority of cases, but with other tree distance metrics, it's much harder to reconstruct these original clusters, which I know are genuine. I made them myself. Another experiment we can do is to take some tree and use that tree to simulate a dataset. And we can degrade that dataset by introducing noise or deleting information from it, and use these progressively more degenerated datasets to construct trees that we expect, as the quality of data goes down, to be further from the starting tree. And that's exactly what we see most of the time with the clustering information distance, but the Robinson-Foulds and path distance again do very badly at displaying this expected behaviour. Another test we can do is to use these tree distances in a practical way to construct a tree space. And we can ask whether the space of trees, which we compress from many dimensions to a couple of dimensions, corresponds well to some extrinsic property of the trees. And one such property might be how well a tree fits to the stratigraphic record. So here, each of the 6 leaves of the tree is associated with a fossil range for a period of time. So time is going to the right here. And you can see that this is actually a pretty good fit with this simulated fossil record. But if we look at a different tree here, we have these really long ghost lineages where we could be seeing fossils but don't. So this tree is a bad fit with the fossil record. It's got a big implied fossil gap. And here's quite a different tree that again fits the fossil record that we've simulated quite well. Well, if we take all 945 six-leaf trees and plot a tree space based on those, project this tree space into 2 dimensions, what we can see is that this tree space is very heterogeneous. So the red colours here represent trees with a good stratigraphic fit, and you can see there are some peaks next to very deep troughs of trees with a low stratigraphic fit. And in fact, these 2 trees that have such a different fit with the fossil record are very close together in tree space, whereas this other good tree is a long way away on a separate peak on its own. If we build a tree space based on the clustering information distance, though, we see a much more natural space with a gradient from high grounds down to low grounds, and our 2 trees with a good fit to the fossil records are close together and a long way from our tree with a poorer stratigraphic fit. So this tree space behaves in an intuitive way. So the clustering information distance is the best metric against a range of theoretical and practical criteria. It can be calculated quickly, and it's implemented in my R package called treedist, which comes with a nice user interface allowing you to make and evaluate your own tree spaces. I hope you can give it a go and let me know how you get on. Thanks.